I will speak about this is a work which started about the question on science evolution. The initial question was to know if we can say something about science evolution by mining scientific literature, and especially in the framework of the cohort analysis. So only looking at statistics on words occurrence, co-occurrence, and transformation of this raw data. And so the methods I will present you, although they first aim at science evolution, there is a later. Okay. What is interesting in these methods is that they can be applied to any kind of unstructured data which are dynamic, unstructured corpora which are dynamic in times, and we apply this to academic literature, but also newspapers, blogs, and now we are working on Twitters and maybe sometimes Google queries. The idea is that all these media have different time scales, and we are interested in seeing knowledge evolution in these different kind of media with these different time scales. So what we will look at now we will look at scientific publication as the source of the extraction of multi-parallel structure. Like, for example, you have authors that could be co-authors, so you have teams of authors, they publish papers here. And inside papers, you can mine the text to get some contents, for example, the n-grams. So you have different trends of research, people that are looking for co-authorship networks, paper networks, and here I will look at the networks we can infer from this set of documents on the semantic side. So when you project the set of over the set of concepts that you can extract from the documents, you can infer the occurrence and co-occurrence and build a graph where you show how these concepts or terms that you have extracted occurs and co-occurs in the documents. And now I will show all what I will say will be working on those graphs. So these are very simple data. It's actually the most simple data you can get, and you can even get them when you look at, for example, in Google's for terms or a couple of terms, it tells you have as many results on that terms, 2 million or any kind of figures, and it is on these figures that the numbers that we do work. So I will go through the reconstruction workflow. So the goals, the ultimate goals of this research is, can we visualize the evolution of knowledge by this kind of data mining? So we want to have a representation of how, for example, if you are looking at science, there are several theories of science in philosophy and history of science, explaining how science evolved by different structure in the paradigms, etc. And the question is, can we see these kind of things or say something from the quantitative point of view from the mere analysis of sets of documents? So here I will quickly describe the different steps to get this kind of visualization, and the final visualization will be inspired by the phylogeny of species, but this will be more like a phylogeny to refer so to memes. So how ID develops and diversify. So the first step is that you start from a corpora and you do some text mining on this corpora to extract some science vocabulary. So for example, we did some study on the field of embryology. So we took here it was on the Web of Science, so we were working on the abstracts and titles of papers from the Web of Science data. And we took about 200,000 abstracts about embryology, and we mine them to extract the vocabulary of embryology science. So you get something like 4,000 keywords or n-grams, which were characteristic to embryology science. And these n-grams, we index them in this kind of corpora to get the graph of, to get the data about occurrence and co-occurrence of this graph. So how many times embryology and morphogenesis co-appear, for example, at a given time. And from that we have a graph whose nodes are the terms, and the link are the number of co-occurrence. These graphs are very poorly informative because it's very simple data, so we can transform this in another graph by computing all the kind of proximity between terms. For example, one of very simple proximity is a conditional probability. So what is the probability to have embryology if you know that the document has morphogenesis, for example? But you have more sophisticated measure. And if you take this kind of proximity, which will depend on what you are looking at, you have some proximities that highlight synonymies and or other proximity measures that highlight the fact that two terms belong to the same domain of research or topic. So when you apply this proximity measure over the matrix of your initial set of terms that you have extracted from text mining, then you get a graph, sometimes directed, where the nodes are your terms and the edges are the proximity between these terms. So the next step is to make some topic detection in this graph. So sometimes it's called clustering or community detection, depending on the scientific community. Here you have different choices. You have overlapping clustering, non-overlapping clustering, probabilistic clustering, etc. I don't enter in the details because what I want to show now is that if you take some simple choice on these different steps, you can still get some very strong results and very interesting results on science evolution. So I will show you a choice of community detection, but this is just the workflow in an accelerated way. So after you have done your field detection, you get some cluster of terms which are supposed to be strongly related all together. So for example, if you think of mapping science evolution, what you want to have is at a very the finer grain level set of keywords that describe a question of research, of a domain of research. So if you meet somebody at a conference and you ask him on what he's working on, then you expect that he will ask you that it tells you that he's working on economy and heterogeneous agents and precedent dilemma, for example. So you have a few keywords that describe the field of research. And then we will look at the dynamics. So now I will give you quickly some example of the different choices that you can have at the different steps to give you the feeling of what you can get after. And the idea is that I will take very, very simple choice here to show you what you can get. So one of the simplest proximity measure, as I told you, is conditional probability. So you can, if NIG is the number of documents that mention the terms I and the term G at on a given period, and NI is the number of documents mentioning only terms I, then you can compute this kind of conditional probability. And if you have a list of terms, you compute conditional probability between all these terms. And you can have a representation like this. For example, if you take genetic networks, you can get all the more generic terms. It means that the terms that given genetic networks, given these terms, there is a high probability to have genetic networks. Again, given genetic networks, there is a high probability to have these terms. So here the terms are ranked by increasing conditional probability from our corpora. So you see you have gene, networks, molecular, complex systems, models, process, etc. And if you take the reverse, so you take the terms such that knowing these terms there is a high probability to have genetic networks, then you go to more specific terms like transcription networks, differential equation networks, motif networks, model, etc. So by having a very simple measure, you can like browse your set of keywords and going from the most generic to the most specific like that, and see how the locally knowledge is structured. Now you can go to topic detection. So here, applying this kind of proximity measure, you have your big graph with all the terms you have identified as relevant, and the link are saying you this term is more specific or more generic than this one, and still very related. And then if you run some clustering algorithm in it, then you can get something like that, where you have cluster of terms that describe some kind of research domain. So here it's, I think it's a click calculation algorithm in this case. So for example, you have public goods and finance, which is shared between two clusters. One is about experimental economy here, and the other is about sustainability and participatory sustainable development. And all these share the question of public goods and finance. So you have small cluster like that identify some domain of research and some domain of knowledge. And using the fact that this measure here is asymmetric, you can try also to give more volume or order in this kind of clusters. So this is an example where taking few words belonging to two, here you have two different clusters around machine learning, data mining, which is here, data mining. And this is a representation of a cluster where you can spatially arrange the different terms in terms of their specificity or genericity to the cluster. So here the coordinates are very simple. For every terms here, you take the average conditional probability of having that terms given all the other, and also the reverse. So here, this is the average probability of having all the other terms given the fact of having inductive logic given the fact that you have all the other terms. So this is this axis here. So this means that if a term is have a high score on that axis, this means that if you know that you have all these other terms, then there is a very high probability that you have the terms here. It means that this is very specific to the domain defined by all the other terms. And on this axis, this is the reverse. This is the average probability of having these other terms, knowing that you have your given keyword. So if, for example, here intelligence have a high score on that axis, because if you know that the documents have, if you know, sorry, it's a reverse. This is the probability of having intelligence knowing that you have all the other terms. So here intelligence has a high score because if you have any of these terms, then there is a high probability that you also have intelligence and artificial intelligence. And this gives you a picture of your cluster, which was flat at the beginning where you have done your topic dictation, when you can say that these are the very large domain defining this cluster, and these are the very specific terms of that cluster. And if you have terms here in the corner. This means that there is no chance of having all the other terms knowing these terms, and the reverse also is true. So knowing all the other terms, you have no chance of having these terms, so these terms would not be relevant to that cluster. And sometimes you have terms here in the corner, but this is very rare because it means that it constrains both ways all the other terms. So when you have a well-formed cluster, usually it's on a line like that. And the height here, so the height of the diagonal measures the integration of the clusters, and we will see how it is in process. But so just this is an example showing that you can have, you run some topic detection, you can have different cluster with some overlapping contents. For example, here data mining, and in that cluster here, data mining is the most generic terms, and the most specific is taxonomy and Chavalarias. And here data mining is inside something more general, which is artificial intelligence. And this has been detected on the period of 2003 and 2006.
The size of the balls is the frequency? Or?
Yes, so here the size of the balls is the log of the frequency, and the color is the speed of the entry of a given terms in the cluster. So if it's red, it means that it's getting denser and denser, and other times it's blue and it's getting out. But this representation is very interesting, and we can look at different phenomena in this representation. So when you have this, many people do some maths after where you see how the different topics articulate between each other. Now we will look at something else, which is the dynamics of these kind of topics. So this is this kind of index. So if you look at the dynamics, most of you know Google Trends or something like that. So you look at the micro levels of just the terms frequencies, and you consider, for example, here Easter. If you look at the occurrence in times, well, you have a very periodic signal. If you look at earthquake, you have very chaotic signals. And if you look at Fukushima, then it's just a very punctual event here. So when you look at that, you say, okay, it's like some interesting things to look at that. But given what we have done previously, and what is interesting is, for example, the link between Fukushima and earthquake, how they are correlated in times, and what's happened around this. And here you see there is two peaks at the same time. So the first thing you can look at is from the perspective of a given keyword. For example, here machine learning, you look at how the proximity of machine learning to all the other keywords evolve. So here this was a study about complex system in general, so the vocabulary was about complex system. And this is the terms which are more specific to machine learning. So this means that knowing machine learning, you have a high probability to have these words. And here, so the color red or green is not relevant. What is relevant is the intensity of the color. So it's just to facilitate the reading. And so here you see that if you look from 1980 to 2006, the first terms which came closer to machine learning were genetic algorithm, natural language processing, artificial intelligence, qualitative reasoning. So this makes like a cluster here of terms. And after you have another orientation around machine learning here, which is knowledge discovery, data mining, industry logic, and combinatorial optimization here. And you have another cluster which appeared at a different period. It's more about intelligent robot mimetism and human modeling, etc. So looking at, from the perspective of a given word, how the other words interact and go closer or further, you can detect the emergence of domain of research and look at their evolution. But this is still at the micro level. So now we look at the meso level. So now we once you have done your community detection, you have cluster of terms that are supposed to represent subdomain of research, or you know that behind these terms there is some papers and work and activity. And what we will be looking at is how this cluster evolves through time. So what you have is that you have different time period. For example, 2000, 2003, 2003, 2006, 2006, 2009, etc. Over every time period, you run your clustering algorithm on your proximity graph between your terms, and you get some topics here. And now you can do some intertemporal matching between one period and the other to see how your cluster have been transformed over time. So different transformation can have been can be observed, and this is inspired by a work from Pala and colleague in 2007. They do this kind of studies over a social network, and so you can have a cluster which is identical from one period to the other. You can have a cluster which slightly evolve and lose one point from, like here. You can have some clusters that are enriched by some terms. You can have clusters that were not sufficiently dense at a given period to form a cluster to be detected, but at the next period they are identified as a true cluster or a true community. And you can also have the reverse, a cluster which is identified as a topic by your algorithm detection or clustering algorithm. And the next step, it is no more cluster. You still have the points, the terms mentioned in the paper, but they are not sufficiently connected to be considered as a domain of research. So if you apply this to literature, and this is an example from the +1 paper, so on the history of embryology, you get this kind of things. So here you have times which flows from here to here, 1981 to 2010. Every square here, we will look at in detail later. Every square here is a community which has been detected. It means that inside you have some keywords that are supposed to be related in the literature and speak about a given domain of research. And the link here are the intertemporal matching links, so they are expressing that between this period and that period, this cluster here is related to that one. So here in that branch, you see a domain which is kind of developing, and at the end having several parallel branches. And this is a way to look at how this kind of subdomain evolves through time. So for every subdomain, we call this a philomimetic branch. It's like a branch in phylogeny, but just for cultural items. And you can easily give a label to a branch. For example, you take the most occurring words in the different cluster here, and in that case it is gap junction, and this gives you an analysis about what the branch is about. If you do this on our corpora of embryology, then you retrieve lots of branches like that. Well, here it's a sample, and for example here you have hair cells and inner hair, fatty acids, cell death, gap junction, cell adhesion molecules, extracellular matrix, and all these are subdomains of embryology. And what you can first observe is that this subdomain has very different dynamics. So some are very bushy, others are linear, etc., etc. And so what is interesting is to do so first it is interesting to have something that from just a set of unstructured documents give you a set of subdomains and look how they evolve. But after you have two directions to further explore the things, either you, in the analysis of that kind of structure, so is there some regularity in this structure? Is there some pattern common common to different kind of branch of science or different subdomain, etc. And the other direction of research that we have taken is the exploration and visualization of this kind of object. So can we use this to just peruse a set of documents and have a better view of what embryology science is, for example. The other things you can do with this kind of structure is to use this structure to overlay some additional information. For example, this I say just passing, but for those who know about science mapping, etc., you will be familiar about this kind of map. So in this here, you have a map where every circle here represents a community, a cluster. And on this map, this is a map about sustainable science. And on this map, we have projected the production of a given scientist. So where you have red circle, it means that some of his keywords are common to this kind of cluster. So it means that he is publishing in that area here. So if you look at the map here, you make evolution through time. You see that people are evolving in their interest. But what is interesting is instead of looking at map, you can overlay this on a phylogeny, and you see how somebody is going through the different branches. And in that case, this researcher was mainly going to that branch and sometimes making some exploration here. So imagine you can overlay a full community of research and see how the community flows through this kind of structure. So this is just an idea. So, so far what we have is that we start from the macro level of terms, where we have the occurrence and co-occurrence. We use some clustering algorithm to identify a set of dense terms that are some meanings. And we did this intertemporal matching here to build a phylogeny. So now we will have a look at some regularities and patterns that we can discover from this phylogeny. So first, one thing that you should be aware of is that so there is choice at the different steps of the workflow. So you decide what kind of clustering proximity measure you choose, what kind of clustering algorithm you choose, etc. So we did several trials to test the robustness. And after you have your clustering, then you do the intertemporal matching. So here we choose a proximity measure similar to the Jacquard. And you say, okay, when two community has proximities stronger than a given threshold, you draw a link, and you have this kind of picture. So now here you have the choice of a threshold, and this threshold is important because if you put the threshold to very high, then you have no link, and if you lower this threshold, you have more links. So the morphology or topology of your branch will vary given this threshold. So all what we will say, this threshold will be represented by this parameter delta, and in all the search for new patterns, we will make sure that it does not depend on that threshold, at least in some range of the parameter. So when you look at a phylogenetic branch, you can classify nodes by different categories. So first you have emerging nodes, or emerging nodes. So they are the starts of a branch, so time flows like that, emerging nodes. After you have branching nodes, where you have like a bifurcation. You can go to a declining nodes, so there is nothing after that. And you have sometimes merging nodes. And any nodes inside which are not emergent or declining will be called steady because they have some father and some sons, and so it's. And the branch age will be the length of branching from that point will be the length from that point to the most ancient emergent nodes. So you know the age from here will be that length here, and the length from here will be that length here. So now we will look at the patterns we can observe given this categorization. Be aware that this categorization depends on the threshold, because if you lower your threshold in the intertemporal matching, then maybe a declining node will have a new sum because it has weak link to it has a weak link, but maybe this one here has no sum just because it has a sum but it's below threshold and we have cut it. So we have to make sure that the patterns we will observe are not too dependent of that threshold. So if you look at the number of branching, merging, declining and steady nodes, depending on that threshold. So the threshold is a proximity measure that varies from 0 to 1, from 0 to 1. So if you put the threshold at 0, it means that you don't know, you accept any kind of intertemporal link. And if you put the threshold at 1, then it means that you cut every intertemporal link. So here you see that when you make this threshold varies from 0.5 to 0.8, there is a lot of nodes of links that disappear, and branching, merging, declining, and steady nodes disappear by an order of 10 in magnitude. So here you have 2, and here you have 0.2. So when you make this threshold vary, you really destructure all the networks. Also, we'll show that you have statistical regularities that are stable across this range of thresholds. So, the first thing that you can look at is to try to characterize your scientific fields. So I remind you that every node here is a set of terms. So inside you have a set of terms which are, there is a link between these terms, and you can compute something on that those links. So one question is, for example, how we can detect emerging fields. I want to compute some index on the cluster and say that this cluster is emergent, or that this cluster is declining. This domain of research here is fading down. So we look at different kind of measure, and so there is different interesting results. But the first measure that we can look at, and we took this one because also it has a historical dimension, is the density. And this was introduced by Michel Calon, which was father of the cohort analysis in the 80s. And so he computes here, it's some kinds of the mutual information. So it's a probability of I knowing G times probability of G knowing I here, and then Ig square over NING. And if you take a cluster, you make the sum of all these measures, and you average by the cardinal. So it's the average product of the two conditional probabilities. And in 91, he has this intuition that this kind of index was characterizing the strength of a cluster. So he says it characterizes the strength of the links that ties the words making up the cluster together. The stronger these links are, the more the research problem corresponding to the cluster constitutes a coherent and integrated whole. It could be said that the density provides a good representation of the cluster's capacity to maintain itself and to develop over the course of time in the field under consideration. So our question is that now, at this time, it did not have all the tools with this large database, etc. And one question was, can we verify this intuition? So we have computed this kind of index over all the cluster here and looking at the evolution. So if you look at the evolution of the index according to the branch age, you see that indeed the index is growing on average over branch age. So here you have branch age for the different thresholds. So you remember this is the intertemporal threshold. So for between 0.5 and 0.8, you remove links, so you are really destructuring all your phylogeny. But still, you have these patterns, and these are error bar, what are standard deviation, and you still see that indeed this density index is increasing on average over a given phylomimetic branch. However, along a branch, you can have many events. You have merging, etc., etc. So, if you go more in the details about this branch, you can look at the different category of nodes to look at their density score. So, if you look at ephemeral nodes, it means that nodes that have no father, no sons, that are just isolated in the reconstruction. You see that they are very low density. And look, this is the error bar. So this is the error bar very, very low. So ephemeral nodes have the lowest density. And after, you have emerging nodes that have low density, but a little higher. Then steady. So steady is all the nodes which have at least one son and one child, one father and one child, which have a higher density. And then when you go to declining nodes, the density is decreasing again. So this suggests that there is like a life cycle of the scientific fields where fields begin with low density, then gains in density, and then decrease. To check that, we will look at the evolution of the density on this kind of segment here. So from the emerging fields until the first branching nodes, and also from the last merging nodes to the last declining nodes. If you look at the density in this from this perspective, you see that indeed you have a very quick increase in density from the first emerging nodes to the first branch, from an emerging node to the first branching nodes here. So from the one here is the normalized density, so it's normalized over the given period. So it's quickly increasing from below average to almost twice the average in that case. And if you start from the last merging and go to the declining nodes, then here it is the reverse. You are quickly declining in terms of density. And this is very robust over 1 order of magnitude in the change of the unit density. So you can look at what is happening between the first branching here and the last merging here, which is you can have other branching and other merging. So what is the history of a field on average between these two events? And we look at what is the behavior of this index locally close to a branching events and to a merging event here. So it's close to that one. So you are looking at the density here. And here merging events is here. So you're looking to the density here. So here 0, you are at the branching nodes. And 0 here, you are at the merging nodes. And you see that you have a tendency to decline and then go back after branching and merging. So this is very on average, because if you look in the details, you can have very many deviation from that. But on average, it's like branching and merging are for the fields like a moment of reorganization, and thus they lose curve consistency at that point, and also sometimes they might just die. So the question is, given that, how predictive is the density of a given field over its future fate in the phylogeny? So if you remove emerging fields, because you see that the behavior near the emerging segments is very particular because you are increasing. So if you remove the emerging segments, then you can see that according in function of the density, the probability to be declining is very, very strongly correlated. If you have a very low density, you have more than 70% and up to 90% according to the threshold chance to be dying the next period. And so when the density of a field increases, then this would drop up to 30%. Which means that if you don't have any information about the future, you only know that there have been some branching or merging even before, so you are on the branch, and you can assign a probability that the next year your cluster will be declining if you goes on with the reconstruction. So this was done on Embryology and another database in Medline. We have to confirm this over different also kind of science, because here in that case it was mostly made on the Medline corpora, but this is a very interesting behavior. So we have other patterns, kind of patterns, but now I want to go to the other axis of research, which is how this kind of research and reconstruction help us to interact with science and with the reconstruction. So we did different studies in different domains, and I will show you 2 or 3 of you. It depends on how many times there is left.
15 minutes.
Perfect, okay. So, the first thing that I will show you is an application to the future and emerging technologies. We have work in the framework of the European projects for future and emerging technologies, so the program, the European program, and about these things of science mapping, etc. And we extracted we got all the proposal to the FP7 program, and we extracted all the author keywords given in this proposal. So we have about 4,000 keywords related to future emerging technologies, or that the proposer thought that they were related to future emerging technologies. We index these keywords in the full Web of Science, so it's 32 million abstracts. And did this phylogeny reconstruction. And this is a sample of what you got. This is about 3% of what you got at the end. So it's very huge. Every branch here is a domain which is related to future emerging technologies. And I will show you how you can bruise this kind of things. So like the switch on the screen, so I will just launch this. Okay. Okay. So this screen is. This is all the phylogenies that I have built on this FET. And what is this one? So here this is just a phylogeny generated. So when you look close to field here, you have, this is a field of that have been detected. So one-way function theory of computation, you have graph algorithm, online algorithm, randomized algorithm, computational geometry, and you see how this evolved. First, if you look at the global picture, you see, as I was saying to you, that there is some very distinct patterns, some bursting here, you have a burst in that domain, and then it is kind of slowing down and then bursting again.
What is the time scale and the why?
So here's the times flow like that from 1980 to 2010. Every square is computed on a 5 years period, and it is a sliding window, so it's going like that. On the top here, you have the name of the branch, which is the most occurring terms, because some terms are occurring several times. So you just label by the most occurring terms. It is just too low to do the thing. And you see that here in this, what is interesting with these FET things is that it is very interdisciplinary. So if you look at the topics, you have quantum, so another quantum things. But here you will have photonics, active circuits, dependent types program transformations, neuroprosthesis sockets, cross-modal integration, etc. So you have very different subdomains of FET, and at once you get all the subdomains that are dealt with FET. Another thing which is interesting is that, so I will take this one, for example. This one is very interesting because this is about neuroprosthesis. So if you go more in time before, you get prosthetic science, but very traditional, like bones amputation, rehabilitation, etc. And here, the color code is the following. When you have something in red, the terms in red, it means that it is its first apparition in the phylogeny. So here, I don't have this display, but I have 6 years that are not displayed because you have a side effect, because if it's the first, you can say it's the first apparition if it's the first year. So this means that this has not appeared the 5 years before. So when it's red, it's first apparition, or when it is orange, it means that it is not the first apparition, but it is new compared to the father. So for example, neurorehabilitation here does not exist in the father. And when it is only black, it means that it was existing just before. So when you have a red label here, this means that there is at least one emergent term, so terms that has never appeared in the phylogeny. When it is orange here, it means that there is no emergent term, but at least one recombination, so it has been taken from something somewhere else. And when it is green, it is just reconduction. And here what you see is, you have neuroprosthesis here, so it was the first try to connect a neuron with silicium. Here you begin to speak about active orthosis. So it means that you have prosthesis, but that can be monitored or controlled mechanically. Neuroprosthesis again, which reappear. And in parallel here, you have another branch, which is totally independent at the beginning, which is a brain-machine interface with research on mirror neurons and cortical interface, brain interface. And what we see here is the merging of the two. So here, you have the merging between the branch of brain-machine interface, which go towards neurotechnology, and the branch of prosthetic science, which go to active orthosis and takes here the name of brain-machine interface, which was a combination from here. And this go to see how you have the merge. If you look at the global picture.
Could you say when this was?
Yes, this was this in 2000 you have the merge, and but you have already some exchange here around the 1970. But since it's a 5 years windows, so it could be 2 years before, 2 years later. I have checked these different events compared to what was appearing, what was the major event in the disciplines. And when you compare, you make this comparison, you can see this. It was on a map which is displaying the Places and Spaces exhibition, so it could be found on the internet, on my website. You see that when you have emerging terms or branching, this corresponds more or less, sometimes you have 1 or years advance or delay, to major events like seminal paper, first commercial application, or something like that. So this is really a good synthesis of what happened around these things. And if you look at the global
the term neurotechnology emerged first?
Sorry?
The term neurotechnology, when did this emerge?
I don't know if here we don't have the terms neurotechnology in the set of these 4,000 keywords, but you have neuroprosthesis here, which emerged first. And it emerged in about 1940. And in the 1940, so this cluster has been computed on the period 92, 96, and in 92 this was the first seminal paper about neuroprosthesis. So this was really over this period that you have this first technology field. And when you look at the global picture, then you see this merging here, and then this expansion here, which is commercial application, etc. Although this is very partial, because this study was not done to study active prosthesis, because it is only the keywords given by scholars to this project. So it is the vocabulary is incomplete, etc. But this is interesting to see that we have this already. And one branch which is a little more complete in terms of vocabulary, because it is in the scope of PhET, it is that one. That one is quantum communication here. And the shape is very interesting, because it starts here, this is the 90s. So it starts with very bushy, in a very bushy ways. And around here, so here it should be 95, something like that, to 2000. So around the year 2000, there was like a slowdown of the disciplines. And these slowdowns goes through two branches. One is about quantum memory, and the other branch is quantum processing, because if you want to do some quantum computer communication, you need the both. And if you look at what, I don't know if it is the reason, because I'm not in the field, but if you look from that phenomenon, why it was coming back to activity, you find this emerging terms, which is EUV, which is extreme ultraviolet lithography, which is a new technology that allows people to manipulate electrons and things like that. So through these new technologies which appear in the two branches here, you see, here you have EUV also on that branch. This boosts the fields, and again you could start the program again. So I'm very curious. Yeah, okay. I'm very curious about specialists commenting these kind of things, but from that you can say some history. And so to end, I will show you another. Okay. Another thing. So. What is somehow frustrating in the last example is that you cannot access to the text. So I will show you another study that we did on, this was for the Ministry of Research in France, and they have asked us a question about monitoring block dynamics. They have a program about health and environment, and they wanted to know if from the blogs you can have early signals or early alerts about some danger for health and for the environment, etc. So we did a prototype, and we took 6 months of blogs here. So we got some data from a professional provider which is used to crawl blogs, etc., and who is called Influence, and they gave us about 10,000 content of blogs over these 6 months. So it was about 200,000 blog posts. From that, so here you have its blogs, but also websites with dynamical contents like online media and website of organization, etc. From this post, we have extracted from data mining and also after from curation, exactly. Here. We have extracted some terms which were related to health and environment. So we have fast food, GMO, work condition, etc., etc. After that, for every 15 days periods, so here you have the period here, we have made this topic detection to identify the topics. And after we have made this intertemporal matching to find the phylogeny of the topics. And so, for example, here you have a topic around, I don't know why the phylogeny does not show us, but I think it's coming. Here you have the topic about agriculture and flora, which is GMO potatoes. There was a polemic at that time because it was going to be authorized by Europe, and in France they didn't want to have this. And transgenic and FNSRA is government institutions. And you can go, yes, here. So it's arriving. And here you have the phylogeny of the debate. So if you look at, so here it's in French, so I translated, but it becomes, the debate starts here. So at that period, and unfold 2 times like that. So for every station here, you have the set of keywords that are relevant to these topics. Here you have the topic. So this is saying that new GMO, NGO potatoes is cultivated in Sweden. And you also have here a measure of the attention of the blogosphere to that particular point. So it's the average number of papers that are, or blog posts which are dealing with that. And the attention is divided into the different arenas or group on the blogosphere. So this is, for example, all the online media. This is European institution, left party, etc., etc. So you can see the evolution of the things. And so this is one particular topics, but what is interesting is that you do the same thing with all the blogs at the same time, and then you go at all the topic at the same time, so you have to wait downloads. But so what you will have is that at a given moment you will have all these streams of attention on the different topics, and when you go inside the streams, then you can look at the history, so the narrative of the debates, what you have exactly, etc. So here, for example, we just were on that link here. So it's a relation between European Commission and France. And you have also terms which are potentially emergent. So don't know, it is a little slow, but you have some emergence stream. So I'll go back to I will show you if people are interested. And just before I finish, I want to show you a stream which is very interesting, and maybe some of you know it. So it's about Mediator. Mediator is a drug. It's a French drug which was used for people with diabetes, but it was also given by medicine to has to help people for doing diet. But it was not it was not done for that. And after they saw that this kind of drugs was hurting the heart. And this made a huge scandal in France because it was given by doctors southern times. It was reimbursed by social securities and it was killing people. And we did this study exactly at the time where this scandal emerged. And so here you see that there was just one post from one online media which was saying that one woman has assigned Mediator to justice because she said that it is this drug has hurting her, but there was nothing particular, just the announcements of the trial. After here you have a leak in the press from a report from the National Health Insurance Organization, which is saying that these drugs could be potentially dangerous. And after you have the publication, official publication of the report with all the different kind of scandals that you have. So you can browse in these kind of debates and see how the ramification of the debates. And from that, so you have this kind of semantic evolution, but you have also the social environment of the things. So this is all the website with a link between each other about these things, and you can go back 3 times or forward 3 times to see the evolution of the thing. And so that's it. So just to conclude that this kind of research, as you see, they could be applied to science, here to blog, which does not have the citation structure or authorship structure. So it is very interesting to be able to apply the same method to the different media. And you have these 2 axes of research. One is really what kind of knowledge we have about evolution of ideas. So is there some regularity in science and our opinions, dynamics, etc. And the other thing is, does this help us to have new interaction with this media, and like this kind of